All right, so today we're going to dive into something you do all the time, probably without even thinking about it, searching. We're going to put two different search methods head to head in a kind of showdown, and you'll see how they solve the exact same problem with, well, let's just say some very different results. I mean, think about it, right? You pull out your phone, you type in a name, and bam, the contact you're looking for just appears. It feels like magic, but it's not. It's actually a really clever, super efficient process, and today we're going to pull back the curtain and see exactly how that magic works. You see, in the world of computers, just getting the right answer, that's only half the job. The real trick is getting it fast. And that's the whole idea behind algorithmic efficiency. It's what makes one app feel snappy and instant, and another one, well, it leaves you staring at that spinning wheel of doom. So let's start our quest. We're looking for something. A contact in a phone book, a number in a spreadsheet, doesn't matter. We need a way to find it that works every time. But more than that, we need a way that is efficient.
Okay, first up in the ring is our first contender, linear search. Now, this is probably the method you'd come up with on your own. It's totally straightforward, super simple, and you know what? For a small, messy list, it's actually perfect. It will always get the job done eventually.
The way this works is, well, it's pretty much exactly what it sounds like. It's like looking for a page in a book without a table of contents. You just start at page 1, then 2, then 3, and you just keep flipping one by one until you find what you're looking for. Simple, right? What's really cool is that we can actually measure how much work this takes. So to find the number 45 in our little list, the computer had to perform 10 separate operations. It looped through 3 times, and each time it had to check the conditions, compare the numbers. We can literally count every single step. So here's the catch. Here's the big problem. What happens when the list isn't just 6 items long? What if it's 600 or 6 million? With linear search, the amount of work grows right alongside the size of the list. It's what we call a linear relationship. And these numbers right here, they really tell the story. When the list gets 100 times bigger, going from 6 to 600, look at the number of operations. It skyrockets by almost the exact same amount. You can just see the workload exploding. And this graph says it all. That steep, straight line just climbing up and up, that means one thing. The more data you throw at it, the longer it's going to take. There's no limit. For the huge amounts of data we use in modern apps, this is basically a recipe for disaster. So this just begs the question, doesn't it? There has to be a better way to do this, a smarter way. And thankfully for all of us, there is. And that brings us to our second contender, binary search. Now, this approach is so much more clever. It's elegant, it's powerful, but it has one very important rule. The list must be sorted first. Now, that sorting takes a little work up front, but as we're about to see, the payoff is absolutely enormous. Okay, so instead of going one by one, binary search plays a guessing game. It jumps right to the middle of the list and asks, is the number I'm looking for bigger or smaller than this one? And depending on the answer, it just throws away half the list in a single step. It's a total divide and conquer strategy. Hey, remember how linear search took 3 loops and 10 operations to find the number 45? Well, because our list was sorted and 45 was right in the middle, binary search found it on its very first try, just 1 loop. The difference is just, boom, right there from the start. Now, let's talk worst case scenario. Even if the number is hiding at the very end of the list, just look at these numbers. For a list with 600 items, linear search could take up to 600 steps. Binary search? A maximum of 10. Just 10. That is the mind-blowing power of cutting the problem in half over and over again. And this is what that amazing efficiency looks like on a graph. It's not a steep mountain to climb, it's this gentle, almost flat curve. That means even if the list size explodes into the millions, the amount of work barely even budges. This kind of super slow growth has a special name. It's called logarithmic. So, it's time. Let's get to the final showdown. Let's put these two algorithms side by side and see just how big of a difference this all makes. This right here is the bottom line. To find one item in a sorted list of 10,000 numbers, linear search might take, well, 10,000 steps. Binary search will take, at most, 14. Let that sink in for a second. 10,000 versus 14. That is the incredible difference a great algorithm makes.
And if a picture is worth 1,000 words, then this slide right here is worth the 10,000 steps we just saved. On the left, you see that brutal, punishing climb of linear search. On the right, that graceful, efficient curve of binary search. This visual contrast, this is why the technology we use every day feels so fast and responsive.
The words here are really important. Linear growth means the work just keeps piling on. But logarithmic growth, that's the magic word. It means the work increases so slowly, even when the list gets gigantic. In the world of software, you almost always want to be on that logarithmic path. So I'll just leave you with a quick question. You've seen the numbers, you've seen the graphs, you've got a huge sorted list, and you absolutely need speed. Which one are you going to choose? It's kind of a no-brainer, isn't it? Of course, it's binary search. And that simple choice, a choice that developers make millions of times every single day inside databases and operating systems and apps, that's precisely why your phone can find that one contact in a flash. It's not magic. It's just a really great algorithm.